All right, so we're going to begin a review of differential forms, which is just enough of a review to get our heads back in the space of how differential forms work in general. And this will allow us to create this new mathematical architecture for the Maxwell's equations. I want to point out, however, that this is a review, right? If you don't know differential forms, if this is the first time you've seen it, then you're really not eligible for this lecture yet. And I recommend that you go back and you study the lecture series in the playlist, What is a Tensor? Which if you haven't studied it, you're in for a treat, because understanding what is a tensor in the way that we present it on this channel is really, I think, fun. It's a delightful experience. We're using the notion of a tensor that really decomposes the idea into components and its basis elements, its basis vectors, tensors as vector spaces, which is confusing just to say, totally needs to be done. So, but if you're here, I assume that you've studied pretty much everything that's in that playlist, but as a math check review, meaning, I'm going to run through a few statements right now, and if these statements don't make a lot of sense to you, then that's sort of an indication that you need to learn the material. The prerequisite to this lesson, which is presumably a bunch of prerequisites to QED. However, this material is not specifically prerequisites to QED. So this is prerequisites to tangential material. How about that? I like that idea. That's what this is. Right now, we are going to engage in prerequisites to tangential material. Anyway, so the idea is, first of all, we are going to consider some kind of manifold, right? And at each point of the manifold, we are going to set up, at every single point, we're going to set up a vector space V. This is the tangent space at the manifold, right? And that tangent space, if you understand tangent spaces, has a basis vector partial mu, because there is a coordinate system here, x0, x1, and all the other x's to the n minus 1th dimension. So we have n dimensions, right? So the manifold has n dimensions, right? We have an n-dimensional manifold, and each point has a tangent space. The tangent space is a vector space. The basis of the vector space are these differential operators. Every tangent space has dimensionality n. Every vector space, for our purposes, will be a real vector space, and the vector space will be endowed with an inner product, right, which produces a real number. And let's see, is there anything else about this vector space I need to write down? I think that's all for now. But every vector space immediately spawns into existence a covector space. And the covector space has a set of basis vectors of one forms, right? These are the big objects of study that are going to come up in this lesson, these notions of one forms, right? The covector space has n dimensions, it's real, and the covector space inherits an inner product, right? It inherits an inner product from the vector space, and then also the covector space, I guess what I should write here is an arbitrary vector v can be expressed in a basis by v mu with contravariant components, partial mu, right? And this is what would be known as a contravariant vector in the standard literature, but a contravariant vector is always connected to a basis vector in the underlying tangent space. And likewise, we should be able to recognize that an arbitrary one form omega, let's do better omega, I think omega is more like that, gives us omega nu dx nu, right? And where this now is a covariant components. And in the literature, you would call this a covariant vector. You may not call it a covector. We will. We'll mix it up. The point is, if you understand it, you can say covector or covariant components of the vector A, right? And then what else do we want to say? Oh, and then once you have, because you have this inner product, right? Because this inner product can be brokered into a one-to-one mapping between vectors and covectors, meaning you can have an unambiguous canonical map from this vector space to this vector to the covector space, as long as the vector space itself is an inner product space. And this will also give rise to the notion of a metric, which is a 0-2 rank tensor, right? So this is a 0-2 tensor, which is the metric. And this metric exists also on the manifold. And the metric's purpose in life is to take two vectors and return a real number. So what I just said, everything that I just said should make perfect sense to you, right? Nothing here should be, oh, there's one thing missing, I suppose. The notation we want to use for the dual space mapping would be dx mu partial mu, right? This is the notation of the covector map identified by this particular basis 1 form acting on the basis vector of the underlying vector space, right? That is going to equal eta mu what am I doing? Not eta, just delta mu nu, right? Delta mu nu. And this down here, this should be a nu. Oops. And that's another, so this notion here is a dual space mapping. This is an inner product. Inner product takes two vectors. A dual space mapping takes a covector and applies the covector mapping to the vector. And we choose the basis of the covector space to be the maps that make this statement true, right? This statement true. Okay, so this is, I guess, the dual, you would call this the dual basis set. All right, so that's our math check. If you know this stuff that I just said very well, then you're ready for today's review. All right, so for those of you who are ready, let's begin. All right, so I've moved up our little math check over here in case we need it, but I've written down a bunch of formulas here that we want to review, and maybe this will be the goal of this lecture, is to make sure that we review these formulas, and then we're going to be in a good position to get our work done. And I think I'm missing one here. I'm missing the Hodge duality. All right, so we're going to try to just get through this. The first one I think we've already done, right? An arbitrary one form can be expressed as this Einstein sum, right? So that's sort of in the bag already. And this is closely related to this formula here, which expresses an arbitrary K form, right? I might just put a little K here to remind us that this is a K form. Well, I better not. I better not put any indices. Indices mean a lot in this business. So just putting random indices without thought is guaranteed to screw things up. But if you leave things without indices and you just assert what they are, then, it's up to people to keep their head on tight and get it down. But let's assume this is a K form, right? So a K form is by definition, a K form has it's a wedge product of one form. So you would have A, wedge B, wedge C, wedge D, where each of these guys here are one forms, right? So this would be a general 4 form, right? And this 4 form, of course, has all of those properties of antisymmetry and everything else you would expect from a bunch of wedge products, right? So, but any arbitrary K form, right, can be expressed this way. And what's important here is this I, right? This I is an index set, and you're summing over this index set. And if you're dealing with a K form, then I is all the permutations from 0 to well, I guess it's all the permutations of the number 0 to n minus 1 chosen k at a time, right, such that the permutation's always increasing, right? So if you have, that's not exactly, yeah, so you dip into 0 to n minus 1 objects, you pull out k. Then you take those k objects and you put them in order. And what you should end up getting is I sub 1, I sub 2, I sub 3, ... to I sub k, because you've pulled out k items. And you've always got to arrange them so that they are in increasing order. Okay, so that's how, and then you take the set of all of those increasing sequences of k indices, and that is your index set I. And you're summing over that index set I. Phew. So the way of saying that is that the basis vectors for a k form, let's just, to make it simple for ourselves, let's do 4 forms, right? Because we're going to work a lot with 4 forms. Or we're going to work a lot with 4-dimensional vector spaces. So this would be, well, let's just imagine we have 4 forms in an n-dimensional vector space, right? So you could have dx0, wedge, dx1, wedge, dx2, wedge, dx3. That would be a basis vector for the set of all 4 forms in, or for the vector space of 4 forms in an n-dimensional on an n-dimensional manifold, or the subspace of the. No, I guess that's the best way to say it. The vector space of all 4 forms, right? But another possibility would be dx0 wedge dx2 wedge dx3 wedge dx4. That would also count because you've chosen 4 one forms and you have an increasing set of indices, 0, 2, 3, 4, right? So all of these become the basis vectors of the vector space of 4 forms, and therefore they each get a component, right? And that component is labeled here. So that's what this sum represents. And there's other ways of doing this, by the way. You can release this restriction of having these increasing indices. The problem is then you need to have then not all of your list of basis vectors are linearly independent, and so you're overcounting, and so you have to include a factor in front of this coefficient, or this sum actually. And if you do that, well then there's this number that follows you around. The price you pay for losing the factor to count for the overcounting is you end up with this index set idea that you have to keep track of. Okay, so that concept is reviewed. And so the next concept we're going to talk about is this D operator. This D operator is the exterior derivative, and we need to know how this exterior derivative acts on functions on the manifold, and we need to know how this exterior derivative operates on one forms, and we need to know how this exterior derivative operates on k forms. And that's these 3 different formulas. So the first formula is f. So remember now, we have our manifold on space-time, right, with coordinate system x mu. So we can imagine a function on that space-time that takes a point x, which I could write as just x because we know it's a full-on coordinate. I could write it as x0, x1, ... to xn minus 1 to show that it operates on, it's a function whose arguments are the coordinates of the manifold. Or I could sort of abuse notation, right, f x mu. And the reason this is abusive is because it almost makes you think like f only takes one argument, and that argument is the muth coordinate of a point, right? But this and these are all supposed to be the same. I could do this, or I could do this. So all 3 of these notations are really supposed to be the same. The point is that f is a function on the manifold, and as such, because it's a manifold, it's a function of coordinates. So if I want to take the exterior derivative of a function x, it is defined in the most elegant and simplest way. Namely, I take the partial derivative of f with respect to dx0, multiply by the dx0 unit covector, and then I just repeat this process for each of the coordinate values. And voila, we have constructed the exterior derivative of, let's say, I guess n minus 1. I know I'm going to screw up this n minus 1 at some point. And we've constructed very quickly the one form that is the exterior derivative of a function f. And notice that's an important point. A function f is itself a zero form, right? And then alpha mu dx mu, that's a one form. So this is clearly in the form of alpha mu dx mu, right, where each of these would be our alphas. And so you've raised the grade of f from 0 to 1. So the 0 is called the grade of the form, right? A 0 grade form, a 1 grade form. You don't use the word grade quite as much in the language of differential forms because you call them forms. You call them 0 forms or 1 forms. So the operation of taking the exterior derivative involves raising the grade of the form. Now, we'll show that that's true in general, right? Taking the exterior derivative of an arbitrary grade form raises it. But here we've just given it by definition, right? This is our definition of how the exterior derivative works. Now, we're not going to go into why the exterior derivative is a thing or what its interpretation is. You may remember there are three different derivatives you can take because we're dealing with a manifold, right? And we're dealing with functions on a manifold and forms. And there's essentially three different kinds of derivatives, right? There's the Lie derivative, there's the exterior derivative, and then there's the covariant derivative. And they all require some different special property in order to work, right? The Lie derivative requires a preferred vector field, right? The covariant derivative depends on the existence of a connection, and the exterior derivative depends on the anti-symmetry of what you're taking the derivative of. So these different derivatives do different things, they have different purposes, they exist under certain conditions, require certain assumptions, or a certain extra elements added on top of the manifold. But we're not going to study that right now, right? We're just trying to basically get the notation down in order to make progress. Okay, so that's the exterior derivative of a function. Now we want to study the exterior derivative of a one form. So the way it's presented here is basically as a rule, right? The exterior derivative of a one form, you execute this sum. But I guess it is worth sort of reviewing where this sum comes from. What I've done over here is I've pulled from the Wikipedia page in the section on exterior derivatives, and I pull down the axioms of exterior derivatives, right? This is how we define exterior derivatives. And df is the differential f for a zero form. We've already gone through that. This here is what they mean by the differential f. And the exterior derivative of something that is already the exterior derivative of a function is actually equal to 0. But what's important is this last one. The exterior derivative of the wedge product between two forms where alpha is a p form, right? They're saying that alpha here is a p form, right? So that is given through this definition. It's the exterior derivative of alpha wedged with beta plus the alpha wedged with the exterior derivative of beta multiplied by this factor in here, this minus 1 to the p, where p is the grade of alpha. So this is the axiom for exterior derivatives that applies to all forms. So if we applied this to a one form, right, and this is the confusing part, right? A one form is omega mu dx mu, right? That's a general one form. So if we take the exterior derivative of a general one form, where actually this general one form really is omega mu, which is a function on spacetime, right? So I'll just put that as a function of x, wedge dx mu. That wedge product belongs in there, where you're wedging a zero form with a one form. It just so happens when you do that wedging, this notion of the wedge product becomes degenerate, essentially, with regular scalar multiplication. So this is what ends up being in here, and then we apply this rule. So we're actually looking for the exterior derivative of this thing. And now that just equals we now follow the formula where alpha is, well, let's see, we follow the formula where alpha is this thing and beta, well, let's see, not d beta, beta is this thing, right? So beta is a one form and alpha is a zero form. So now following that formula, let me clear up the formula so you can see it. Following this formula here, d alpha becomes d, let me go back to red, d omega mu of x, the exterior derivative of omega, the component, wedged with dx mu, right? So that's this term here has now become that term there. Should do this in green, right? This term here is now this here. And then I get minus 1 to the 0 is minus 1 to the 0. Well, I guess what I should write is I get plus minus 1 to the 0. So I get plus 1. Well, I'll just write it all in, minus 1 to the 0. And then it's alpha wedge d. Well, alpha is omega mu of x wedged with the exterior derivative of b. Well, the exterior derivative of b is the exterior derivative of dx mu, right? So now we have this term. And this is the answer for the exterior derivative of the one form omega, right? That's this answer right here. But the key to understanding how this works is that the exterior derivative of an exterior derivative is equal to 0 by this axiom here. So that means, and this, by the way, is just equal to 1. Not that it matters because this guy being 0. So this whole part goes away and you're just left with this. But the exterior derivative of omega mu is, we've already seen, right? It's partial nu omega mu dx nu. Ergo, the exterior derivative of a one form omega is now partial nu omega mu, which is a function of x, right? So these partials make sense. Dx nu wedge dx mu, right? So this is the formula for the exterior derivative of a one form after you've kind of, but it's derived from the axiomatic recursive definition. I say this is recursive because, you have the exterior derivative of the form A and the exterior derivative of the form B, and that's a P form, so you're going to have to now go through this process for the P form. But for a one form, we can kind of write down this nice little neat formula, and that's what this formula is. So we've now covered the exterior derivative of a one form. Let's see, what else have we covered? We've covered the exterior derivative of zero form, of a one form. We've defined a one form. We've also, I guess, defined V, a vector, an arbitrary vector, is V mu partial mu, right? Just like an arbitrary one form is this, an arbitrary vector is that. Okay, so what's next? So now we want to look at the exterior derivative of basically an arbitrary K form, right? And you get this nice formula, which is quite reminiscent of this formula, right? You have this partial derivative summing with an index that sums into this first term, and you have this sum over these ordered indices now. So let's see if we can understand this simple expression using our kind of basic algorithms over here. So I'll begin just by writing down alpha, right? Alpha is this sum over these indices, this index set that we've already discussed of the alpha index with the K-blade dxi. So this is good for any K-blade. So we're not specifying the index set very particularly. We're just saying it's that set of increasing indices of K coordinates pulled out of an n-dimensional or a possible choice of n different coordinates. And this is in green because I'm going to kind of ignore it, and we're going to think of this as an Einstein sum. So we're going to get rid of this summation. So now we'll just sort of apply this general idea of how to create an exterior derivative of the wedge product of two forms, and we'll do the same thing. We've got this constant, or not constant, this function on the space-time, right? Because remember, these are all fields, right? This is a form field, so there's one form at every point in space-time, so this is a function on the space-time. It's hard to remember that underneath all of this is a manifold, right? Which in our case is going to be space-time. And the manifold has coordinates x mu. You've kind of got to always remember that. And at every point you have a value of this form, and ergo you end up having a form field, and that is why this guy, alpha I, is alpha sub I, is actually a function of the coordinates. I know I said that before, but the problem is as you move away from it, your mind drifts off of it and you tend to forget. So saying it again can't possibly hurt. So that's the reminder. This is a form field, and we're going to express it just like this without the summation. All right? So now we take this guy and we treat it very much the same way we did before. We are looking for d alpha, which is going to be d of alpha I dxi, which is equal to d of alpha I, the zero form, wedged with dxi, which is the k form, right? And we know how to do, now we are set up. This sets us up to use this expression here. So this is d of alpha I wedge beta. So beta is played by dxi here, right? So beta is dxi, alpha is alpha I. And I guess I'll stick with green. This becomes plus minus 1. And again, we have 0 because alpha I, this p is the grade of alpha, which in our case is 0. So minus 1 to the 0 will be 1. And then you have alpha I wedge with d of beta, but that's d of dxi. And as before, this goes to 0 because you have the exterior derivative of something that's already an exterior derivative. So that's based on this principle. So now we are left with the first term itself, but we know how to do the first term. It's alpha nu, well, let's see. I'll go with eta alpha I dx eta wedge dxi. Phew. And this with the implied sum over I, which comes up front, this is d alpha, right? And that is, so this is the glorious final formula, which is exactly what we wrote right here. So now we can take the exterior derivative of an arbitrary form alpha. Okay, good. So what next? Well, I think next we should just do an example, right? So let's take a look at this particular two form, right? Alpha is a two form, and the two form, we're going to say alpha is equal to a coefficient a, which is a function in space, right? A is a function of x 0 through xn, right? And I'm not specifying, well, I guess I'm going to say we're in 5-dimensional space. I'm going to pick a number, and it is 5-dimensional space, say. And let's see, no, I mean 4-dimensional space. N is going to be 4-dimensional space. So this is 4, right? And likewise b. b is a function of x0, x1, x2, and x3, right? So this particular two form is a times dx0, dx1, and b times dx2, dx3. So that's a two form, right? And that is in the form of alpha I dxi, right? It's because we've indexed things correctly, right? 2 is less than 3, 0 is less than 1. And it just so happens that the other combinations that are allowed, right, x0 wedge x2 and x0 wedge x3 and x1 wedge x2 and x1 wedge x3, those coefficients are just 0, right, in this sum. Those alpha i's are 0. Okay, so we've chosen a two form, and we're going to take the exterior derivative of this two form. So we'll just write that down, right? We're going to take the exterior derivative of our two form. Now this is linear, so we're going to break up this sum, right? That's the equivalent of taking this big old summation symbol and breaking it up into its explicit parts. And the exterior derivative is linear, so this is a good opportunity to point that out, right? Derivatives, anything that pretends to be a derivative is linear. And so it's going to be the exterior derivative of the total two form is the exterior derivative of this first component and the exterior derivative of this second component. So now let's look at the exterior derivative of just this first component. The second component is obviously going to be the same process. The only difference is changing some indices and the letters. So we use our basic formula. So the exterior derivative of this thing is the exterior derivative. Well, first of all, we take the a and we call it a 0 form, and we just wedge it right in with the basis vector. And then we use our formula from, I guess, the formula from Wikipedia, right? This old Wikipedia formula right here, this guy. And alpha now becomes a, the 0 form a, and beta becomes the basis of the basis vector in the K-form vector space. And so we're going to take the exterior derivative of a and wedge it with dx0, dx1, this basis vector, which is this thing here, this dx index I, right? And then we're going to add to it minus 1 to the 0 power because a is a 0 form. Then we're going to take a and wedge it with the exterior derivative of this basis vector. So we can speculate that this is going to be 0. If you doubt that this is 0, because the rule strictly speaking is ddf equals 0, right? But if you execute this formula here recursively, right, then you discover that the exterior derivative of anything that is already the exterior derivative of something will ultimately be 0. So let's see. So this part goes away. And now we're left with this part. So now we take the exterior derivative of this function a, right? And that is the exterior derivative of a function. It's this differential of the function. So that's a beautiful part of our algorithms, right? The exterior derivative of a function is the differential. This, in regular calculus, this is called the differential of the function a. I guess that's where this language comes from. But we're in four-dimensional space, so we have to do this for four different, spatial coordinates, right? And that guy is essentially, well, it is not essentially, it literally is. It's partial nu alpha dx nu, right? That is what this sum is right here. And then when we open up that sum, we wedge it with this original indexed vector. And what we notice right away is, again, this is linear, right? The wedge product is linear. Another good chance to point that out. So you have dx0 wedged with dx0, dx1. And now you have to realize that whenever you see dx0, dx0, dx1, whenever you see a repeated vector inside of a wedge product, you know right away that the wedge product is 0, right? So this is a good place to point that fact out. So this term goes away. Likewise, this term goes away because dx1, right, doesn't matter what order the wedge products are in. If any two of them are the same, this whole thing goes to 0. So those two go away. But these two survive, and you end up with dA dx2, dx2 wedge dx0 wedge dx1, and dx3 wedge dx0 dx1. So these two survive. Now the only problem is our final form doesn't really satisfy our increasing index rule. We want these indices to go up. So, but the only possible way is you're off by a sign. So I can rearrange these things as long as I keep track of how many swaps I make. That's an important thing to remember, and this is a good chance to review it. I'm glad we did this example. So this, if I move dx0 over here and dx2 over there, that's one swap, and that introduces a sign of -1. And then I have dx0 wedge dx2 wedge dx1. But then I do another swap, and I get dx0 wedge dx1 wedge dx2. And that's good, but I've introduced another -1, so they all cancel. So because of that, I can elect to simply reorder this as dx0, dx1, dx2. So, and I don't have to worry about any signs. So I just do that. I go dx0, dx1, dx2. Now over here, is it the same? Well, here I have to, let's see, what do I have to do in this case? Let's see if I can just do it straight up in my head. dx0 and dx1, these two are already in order, so it's just a matter of moving d3 all the way over. So that's one swap for -1 and another swap for -1 again. So this is actually already, there's no additional minus sign introduced in this either. So I get dx0, dx1, dx3. All right, so there's no example in this particular case of introducing a minus sign. So, and then this final answer, right, this is the exterior derivative of d alpha, right? This is the answer. And notice that alpha was a 2 form, right? We started with alpha as a 2 form up here in the new red boxed equation. And down here, its differential is a 3 form, right? And that's because the exterior derivative always boosts your form by 1. Okay, so that is that. That covers, that covers that with an example. Let's see, what were these other two? This is just maybe I should have done this one earlier, but if omega is a k-form with this, using this sort of Einstein sum notion over an index set of increasing indices, And lambda is a one form, right? This is a one form right here, because mu is just a regular old index, not a index set. Then the wedge product of this k form with a one form is simply the product of these two coefficients, and then the k form part is just wedged with the additional one form, right? So this is a pretty simple and straightforward formula. And then here we have the sort of the expanded version of ddf of a function equals 0. We have the exterior derivative of any already exterior derivatived form equals 0. I'll just bite the bullet here and review the actual language, right? So here's the way this works. If you have a form omega and d of omega, the exterior derivative, why isn't this writing? The exterior derivative the exterior derivative of omega equals 0, right? Then omega is called closed, right? Omega is closed if its exterior derivative is 0. Now, if gamma is equal to the exterior derivative of some omega, so remember, omega would have to be, if gamma is k, is a k form, omega has to be a k minus 1 form, right? But if gamma is the exterior derivative of some k minus 1 form, then gamma is exact, right? So that's the two words we're using. So here, I'm basically saying, right here with this expression, I'm saying that the exterior derivative of any k form omega is closed because the exterior derivative of the exterior derivative of something is 0. So, however, if I had written this as omega equals, gamma equals d omega, and then I wrote d omega equals 0, right? I would say two things about gamma. I would say gamma is closed because its exterior derivative is 0, but gamma is also exact because gamma is the exterior derivative of a k minus 1 form. And this basically is saying that all exact forms are closed, right? So there, we've bit the bullet and reviewed the language. The profundity of this goes way beyond my little daft explanation here, or I'm not even explaining things, I'm just defining things. These little definitions and these words are not trivial. This is a very, very profound concept in differential geometry. But for our purposes, we just need to understand that closed forms, that exact forms are closed, right? Exact forms are closed. Okay, what am I missing here? Okay, so this review so far is missing the notion of Hodge duality, right? And that's too big a topic to proceed with now. So we will begin duality. So we will begin our next lecture with a review of Hodge duality, and then we'll be set up to do I think we'll have everything we need to do Maxwell's equations. All right, so I'll see you next time.